Hey, so we're just going to go over the spring 2021 final question number 5. So looking at part A, it's asking write operations are typically more time consuming, so you only count the number of pages written to a disk when you count IOs. So this answer is false because remember that when we do IO costs, we include both the reads and the writes counted. In part B, we're asked to fill in the blank. In variable length record formats where we use a record header, we store the fixed length fields before or after the variable length fields. So this is from lecture and from our notes. We would want to store the fixed length fields before the variable length fields. And then this ties into part C, which is asking, where do we store the pointer to the variable length fields? And we want to store it at the end of the variable length fields. So for a variable length record format, we'll have all the fixed length entries. And then for every variable length entry, we'll maintain a pointer to where that variable length entry ends. And we'll store that in the header for that particular record. Part D asks if you have a packed sorted page with 13 fixed length records, each record is 10 bytes long, and you wish to delete the second to smallest key on the page, how many bytes will you need to change on the page? So we know that we're removing the second to smallest key, which means that since we're maintaining a packed sorted page, this will be the second from the top record, and all of the remaining records on the page will need to shift up to fill in the spot that we created when we deleted a record. So that would mean that right off the bat, we know we need to have at least 110 bytes need to be shifted up because it's 10 bytes per record and we're shifting 11 records. But we have to take into account that there's also a header page, or there's a header value at the beginning of your page. And since we have a packed sorted page and our records are fixed length records, all we need to maintain in our header is how many records are on that page. So that's just going to be an int, and an int is 4 bytes. So we just need to add 4 bytes for the header, which needs to be updated now. And that means that our sum is 114 bytes are being changed. All right. Part E asks, in an unpacked page with variable length records, it can hold 4 kilobytes, which is 4,096 bytes. Assume that a page has 6 bytes of metadata, and you save the rest of the page for the records and for the page footer. If the page is initially empty and Jerry decides to insert 2 records, one of them 20 bytes long and the other 40 bytes long, how many bytes of free space is remaining? So we'll just start by going through each of the different parts of the page and thinking of how many bytes they'll take up. So we start with 4096 bytes, and we need 6 bytes for the metadata. So that leaves us with 4,090 bytes. Now we have to have a footer on our page because we have variable length records. The footer has 2 fields that we keep track of regardless of how many records there are on the page. And the first is the slot count, which is an integer. So we're going to have 4 bytes for that. And the next thing we'll need to keep track of is a free space pointer, which is pointing to the last record and showing where our free space begins. So that's going to be another 4 bytes because it's a pointer. So we've taken care of the slot count and the free space pointer. Recall that the footer also has 2 values for every record that's kept. One is a pointer to where that record is, the beginning of it, and a second is the length of that particular record. Both the pointer and the length are 4 byte values. So for each record that you have in your page, you need to keep track of 8 bytes of information. We have 2 records that we're inserting, so that's 2 times 8. That's supposed to be a plus sign. So we have 16 plus 4 plus 4 is 24. And the only thing that's left now that we've taken care of our footer and the metadata is just the length of the records themselves, which is 20 plus 40, which is 60. And that makes our result be 4,006 bytes left on this page for free space. And we just got this number by taking 4096, subtracting 6, subtracting 24, and then subtracting 60. Part F asks, suppose you have an unpacked page, you have an unpacked page with variable length records that currently holds 20 different records and has 1,000 bytes of free space. If you delete one record with the size of 50 bytes, how many bytes of free space do you have immediately afterwards? And then ask also for what your slot count is going to be immediately afterwards. So we start off with 1,000 bytes of free space. We're deleting one of the records, and that record is 50 bytes long. So that means that we have freed up 50 bytes of space right away. So we know at least we're going to have 1050 bytes of free space. The tricky part of this question is in the slot count. So even though technically now this record has been deleted, the slot count, that field will just be nulled. We actually are not going to free up that particular value because we will just keep it as is, but we'll just null the value itself. So our final answer will just be 1050 bytes. We won't need to add 4 to say we freed up that particular slot count. Oh, so I think that it also asks for the comma, the slot count. So your final answer would look something like 1050 and then 20. Okay. Now for part G, it asks which of the following types of pages may encounter fragmentation. So fragmentation, remember, is when collectively your page has enough free space to add another record, but that free space isn't continuous, so we can't add a record into our page unless we reorder the records in the page to be either packed together or we make enough space in our page for to insert the new record that we want to. So as I said, if you pack the records together, that would free up the space that you have on the page to insert your new record. So packed pages don't have the problem of fragmentation. Additionally, if you have fixed length records, you know exactly how long each record is going to be. If a record gets deleted and you decide to add a new record in its place, they're going to have the exact same length, so they'll fit in each other's spots. So fragmentation isn't a problem again when we have fixed length records. This leaves the only answer with being unpacked pages with variable length records, because those may have gaps in between there where maybe one of the records you deleted was slightly smaller than one you intend to insert, and you may not have the free space consecutively on your page to insert the record you want to. The answer for this one is just unpacked pages with variable length records. Part H is asking, in a page directory for a heap file, you have 2021 data pages. Assume each header page holds information for up to 200 data pages. If you have the least number of header pages possible, what's the maximum number of IOs it could take to insert a record, assuming that at least one data page has room for said record? So we're thinking about the worst case situation in terms of IOs if we have the least number of header pages used to represent our data. So what's the least number of header pages used? That would just be, you have 2021 data pages, and each page can hold, header page can hold up to data for up to 200 data pages. So that would just be the ceiling of 2021 divided by 20, which would just be 11 pages, 11 header pages. Since we're thinking of in terms of worst cost IO, the worst case situation for this would be you have to read all the header pages because only the last header page has a pointer to free space enough for the record you're trying to insert. So right away here, we would incur 11 IOs. Let's write this down. All right, now that you've found the header page which has the correct pointer, you're going to have to do several reads and writes to update the information. We're going to need one IO to read the page where the data is located, update the page, so we'll need to add the record that we want to at that particular location, write that page back into memory. And now that we've changed where that free space was on your header page, you need to also update that header page as well. So we're going to incur one IO for reading the data page, one IO to write the data page with the new updated record, and then one IO to update the header page. And this results in 14 IOs total. In part I, Jerry is writing goodbye notes. As he writes each note he enters into a database, and the schema includes the recipient's name as the primary key, the note's message body, and the address of the recipient. After writing all the notes, he plans to scan through them and send them out each to the listed addresses. What type of page and file format combination is best for his use case? So in this situation, we don't have any deletions going on. We're not looking to read a particular letter once it's been added into the database because he's just going to scan through all of them and send them. So we don't need to maintain some sort of sort or a way for us to quickly look up a particular record. It's just a waste of time for us. So we're not actually going to worry about doing a sorted file. So that eliminates the second two options. And then in terms of packed versus unpacked, we don't have any deletions happening. We're just going to be inserting records into our database and then reading them all from start to end. So an unpacked page is actually going to be the best situation for this because it'll make the most use of the space that we have available on the page. Sorry, if I said unpacked, I meant to say packed page is going to be the best one you want to use. In part J, the situation changes a little bit. Jerry realizes that he might like to update some of the notes after writing them, but before sending them out. He would like to be able to quickly retrieve the corresponding note and make the adjustments he wants. So now in this situation, unlike before, where we didn't care about where things were stored on the page because we're going to be scanning through everything, we might want to look up a particular note or a particular record in our database quickly. So maintaining a sorted file on primary key, so if Jerry knows exactly whose name he's looking for, he can quickly look that up, might be really helpful for us. So it would be a good idea to maybe make it a sorted file. Additionally, he's trying to change the note and change the message body itself. So that actually makes this we originally had variable length records, but now in our file itself, he might be changing the length of the record once it's already been inserted into the file. So if we try to maintain a packed format again, if he changes the value and he has to remove it to a different spot where there's enough space for that record, we'll have to shift all of the data up again to make sure that we have a packed format. And that's a lot of work and it's kind of a waste of work. So it would make sense here to make it an unpacked file, but make it a sorted unpacked file. In the last part, Jerry has received many notes as well, and he'd like to store the notes he received in a different database with the sender's name as a private key. And in the future, wishes to read the notes from friends when the person's name pops into his head. So we need to maintain some sort of order again, like we did in part J. We quickly look up a particular record based on the person's name. But unlike in part J, we're not modifying a record. We may not be deleting anything. So it isn't extra work for us to maintain a packed table format and make the most of the space that we have available. But we do want to maintain a sorted file so that he can quickly look up the names that he's looking for. So that's why we would choose the packed sorted file as the best option for us. And I think that's all.